Hi folks, we're going to take a look at number 11 on page 120, which is similar to number 12. So here we have a family of cubics with zeros 1 plus root 2, 1 minus root 2, and negative a half. Okay, and then in the second one, they want us to find the specific member of that family that passes through 335. And I think what might have been confusing some of you was the answer in the book. I guess they do say in the question in simplified form. They actually get quite a nice answer, but it takes a fair bit of time because you have to do some expanding. So what I'm going to do is I'm going to first solve the problem the way the way I would expect. I think it just doesn't make sense to do all that expanding, but then I will do it at the end, show you how to do that problem if you're interested. Okay, so here I've got a family of cubics, okay, with these zeros. Now since there's 3 and it's a cubic, they must all be order 1, although we did say that if it doesn't say order 1, we assume it is. Okay. The only difference here is that our x-intercepts just happen to be numbers that are not quite as nice as regular old polynomials. Okay, so we can still though use our exact same method as before. So here 1 0 is going to be x minus whatever the, one of the factors is just going to be x minus whatever the x-intercept is. So in this case here, 1 plus root 2. So notice here I'm subtracting the whole number. Make sure you have those brackets in there. A second factor will be x minus the second x-intercept, which is 1 minus root 2. Okay. And now here, this is where I have a bit of a choice to make, is I could write x minus negative a half, okay? But since this is a nice fraction, I know that a factor that will give me a 0 of negative a half is just going to be 2x plus 1. Okay, so if you solve 2x plus 1 equals 0, it's just going to give you negative a half. Okay, so it's just easier to not have to work with this fraction. Okay, so this is a function that has these 3 zeros, but of course there's infinitely many of these functions. I just have to stick an a in front to get all possible members of the family. Now we should really specify here that a can't be equal to 0. Okay, now you'll notice in the notes that I use a different notation for this. I say a is an element of all real numbers, so a can be any real number, but when I just want to get rid of one element, I can say except the element 0. So this means a can be any real number as long as it's not equal to 0. Okay, basically means the same thing. Okay, so this is what I would expect you to do if I was asking for that answer. So let's go to B here. Okay, now we can simplify things a little bit. So first of all, I'm going to input my x and y values. So here, x is just going to be, my y value is just going to be 35. Here, a is that thing that we're looking for. My x value is 3, and I'm subtracting 1 plus root 2, so I might as well distribute the negative 1. So it's minus 1 minus 1 minus root 2. Then here we have x equals 3, and then minus again 1, and here though it's going to be plus root 2. Okay, and then here let's replace x by 3, so 2 times 3 plus 1. Okay, and let's do a little more simplification. So what do we have here? We have a times 3 minus 1 is 2, so we have 2 minus root 2. Here we have again 3 minus 1 is 2, 2 plus root 2, and then here 2 times 3 is 6 plus 1 is 7. Okay, we can still simplify, and this is where we get a chance to use some of the stuff you learned in grade 11, in particular working with radicals. Now remember that when we have a radical in an expression and we're doing algebra with it, we can sort of treat it like it's just a variable. So here, hopefully you notice that this looks exactly like something that gives us a difference of squares. Okay, so here we've got 2 times 2 is 4. Here we have 2 root 2 minus 2 root 2. The middle terms cancel out. And so then I've got minus root 2 times root 2 is just 2. Okay, and there we go. This is starting to look pretty nice. So 35 equals, and what do we have? 4 minus 2 is 2 times 7, which is 14, so 14a. So a is equal to 35 over 14, which of course we should simplify. Divide both by 7, 5 over 2. Okay, so the answer, sort of in, I guess, this less simplified form, would be y equals, so our a value is 5 over 2. Okay, and then our other components here, and I might as well simplify a little bit. I'll distribute those negatives here. So here we have x minus 1 minus root 2. In the second one we have x minus 1 plus root 2. And the last one we've got 2x plus 1. So this is what I would expect as an answer. Okay, so if you don't want to go any further, I would stop here, but I will continue and see how could we come up with this here so that it's in a nicer form. Okay, so I'm going to go here and redo A. Okay, and the first thing I'm going to have to do is I'm going to have to do some distribution. Okay, trust me on this one, it's much easier to do this distribution first. So we'll forget about the A. Keep that on the outside. But what I'm going to do is I'm going to multiply these two binomials. Okay, so this is where we're going to take it slowly. Okay, so what's the first term? That one's easy. It's x times x is x squared. Okay, then I've got x times the negative that, so it's minus x times 1 minus root 2. Notice how I'm not distributing the x. You'll see in a while why not necessary to write that out. Next, I've got the inner terms here. So again, minus x times 1 plus root 2. Okay, and lastly, these two, first of all, the negative signs are going to become positive, so plus, and look what I have. I have something very similar to what I had before. I've got these two expressions that will give me a difference of squares. So what do I have? I have 1 times 1 is 1. The middle terms cancel out. Negative root 2 plus root 2. So I just have root 2 times negative root 2 is just minus 2. Okay, so there's my expansion of these two binomials. Now you may sort of think, well, this still doesn't look pretty good. So let's keep going. Have faith here. So here, this x squared, nothing to do here. But remember, when you're subtracting two like terms, you're really just subtracting their coefficients. These are just the numbers. I just happen to have written them up in front of the, after the x, but they could easily go in front. So let's see what we have here. We have negative 1 minus 1. So we have minus 2x. Sorry, that's x squared. Okay, but look what happens here. We have positive root 2 minus root 2. Lo and behold, the root 2's cancel out. So I'm just left with minus 2x. And then here, 1 minus 2 is negative 1. Okay, and now I've got 2x plus 1 here. And suddenly, this is not the most fun expansion to do, but it's significantly simpler than having a whole bunch of square roots in there. So here, y is equal to a times, so let's multiply this out, x squared times 2x, so that's 2x cubed, x squared times 1, so plus x squared, negative 2x times 2x minus 4x squared. Then we've got negative 2x minus 2x, so minus 4x. And then here negative 1 times 1 minus 1. And let's just clean this up. So we've got 2x cubed plus x squared minus 4x squared, sorry, so this is minus 3x squared, and then, well, we already calculated the 2x, so minus 4x, and then minus 1. Okay, and so here's our family of functions in standard form instead of in factored form, and if we wanted to write the answer in B, well, we actually already found that A value, so there's no point in doing it again. It would just be 5 over 2, 2x cubed minus 3x squared minus 4x minus 1. Okay, And if you were to, re-input 3 and 35 into x and y, you see that you would get 5/2, but I'm not going to redo that again. Okay, so I don't expect you to do all this expansion, but it is a little exercise in algebra and, carefully using your knowledge of radicals. Okay, so that's it for this one. Bit of a long one this time.